mk sine of hyperbolic ml minus mx divided by cos h ml plus h by mk sine hyperbolic ml. And for the heat transfer, to the fin, we will have this under root hp kac times theta b times sine hyperbolic ml plus h by mk cos hyperbolic ml divided by cos hyperbolic ml plus h by mk sine hyperbolic ml. Alright, so this is the thing we should consider, but we can see that these expressions look like very tedious, and so there is one more alternative way to solve this problem, that is the corrected length approach. And we can use both methods to find the heat transfer and temperature at any location. For this case, where convective loss from the tip is considered, so in that case, what we need to do is to let me write first. Corrected length approach. In this method, what we are doing, the philosophy is that if this is the actual fin of length L, and we are considering the heat transfer from the lateral side as well as from the tip, so to model the heat transfer from the tip, the philosophy is that add extra material to this fin which will contribute to the same heat transfer as that of tip. Add extra material in the longitudinal direction to this fin which will contribute to the same heat transfer which will from the lateral side, which will contribute to the same heat transfer as that of the heat transfer from the tip, but keep the tip adiabatic. Alright, so how much we should add this length? So this length should be having the same heat transfer from the lateral sides as that of this Q-tip, right? That means that Q-tip heat transfer from the tip side should be the same as the new material which we have added to it, right? So which is nothing but h times parameter of this fin and this small l delta L times temperature drop, and this fin tip is H times AC cross sectional area times delta T HPL delta HP delta L times delta T. So we can find how much length we have to add to this original length, and this will be the corrected length, means new length. So this is nothing but the cross sectional area of the fin divided by parameter of the fin that we have to add. How much length we have to add is answered by the cross sectional area and the parameter of the fin. Alright, so in all the expressions for the adiabatic fin, heat transfer and temperature profiles, we should use this length, and this is the easy way as compared to using these tedious expressions, right? So we have the expressions for adiabatic tip heat transfer already, right? Like, let me write cos H m L minus x divided by cos hyperbolic ml, right? So in these expressions we should use L as LC when for convective heat transfer from the tip. Okay, and for the fin heat transfer expression we should use under root HP KAC KC times theta b times 10 hyperbolic ml, in which length we should use corrected length. Alright, so I hope you have understood the philosophy, which is in summary is that adds length to the original fin, which will give the same heat loss which will be given by the convective heat loss of the tip from the fin. Okay, and assume the fin tip as insulated. Alright, so there is one small thing we should know before moving forward. If this h by mk is generally the square root of Biot number, so if h by mk is very high, means is greater than 1, then fin act as insulator. And if h by mk is greater than 1, that means h is low. And k is high. In that case, if we add the heat transfer, if we add the fin, then it may give the advantage of increasing the heat transfer. Alright, so fin act as heat conductor. In that case, if it is equal to 1, then no use of fin. Means even if you are using the fin, then it will not increase the heat transfer. That will be the physical significance of it. So next we will try to develop some standard criteria. Then what are the indices to measure the fin performance? That, let's say if we are adding the fin but Is it really increasing the heat transfer or not? We have to check now. So what are the indices? What are the parameters that we need to check to the to measure the effectiveness and efficiency of the fan? All right. So signing off for this lecture. So see you in the next one. Thank you.